The next example in the textbook shows how you might handle a case where there is uncertainty around the activity times. So here it is, our PortaVac project. So here's a company considering manufacturing a new cordless vacuum cleaner. It's called a PortaVac, and they want to do a feasibility study for this product, and they want to know how long the feasibility study will take. And activities for this study are given in this table. Now notice that for each activity we have 3 numbers for the duration rather than 1 number. This is because we don't know exactly how long each activity will take. So the idea is, if you don't really know the right answer, you should give 3 answers. That is, the shortest possible number, the smallest possible number, and the highest possible number, and the most likely number. That way you will have much better chance of being correct. So for instance, for A, activity A, what they have is that the shortest possible time is 4 weeks, but in the worst case it might take as long as 12 weeks, but the most likely to take about 5 weeks. So for each activity we have these 3 time estimates: the optimistic time, the shortest possible time, the pessimistic time, the longest possible time if we encounter significant delays, and the most probabilistic time, that is the most likely time the activity will take under normal conditions. Since we have only these estimates for the activity times, we will not be able to determine exactly how long the entire project will take, but we will be able to say something about the probability we will finish by a certain time. Specifically, here are the kinds of questions we'll be able to answer, like the mean, the average, or the expected time for the project, standard deviation for the project time, and the probabilities the project will be done by a certain time, 20 weeks, 16 weeks, and so forth. So how we do this is we assume that each activity duration is a random variable with a beta distribution. Beta distribution has 3 parameters, A, M, and B. And with these 3, we could find the expected time and the variance for each activity duration. Beta distribution looks something like this. Here's the axis. Here's your shortest possible time, and then the most probabilistic time. Then we have the longest possible time here. So here's the A, and the peak is the M, and the right endpoint here is the B, the longest possible time. Okay, so that is your beta distribution, and we have the formulas for the expected time and the variance. So now for illustration, I'm going to put here a couple of activities, let's say A and B, and put down the corresponding parameters. So A, for the activity A, the shortest possible time was 4, most likely time was 5, longest possible time was 12. Activity B, it was 1, 1.5, and 5, and then for C is 2, 3, and so forth. Okay. Now what we'll do is we will use these formulas to get the expected time and the variance for each activity. So let's see. So expected time for the activity is A plus 4M plus B divided by 6. So that's kind of like, that's basically the weighted average of A, M, and B. Here's weight for A is 1, weight for B is 1, and weight for M is 4. And here 6 is a sum of the weights, 1 plus 4 plus 1. Okay, and the variance is B minus A over 6 and square the result. So let's just do a couple of practice calculations. Let's say if you wanted to get the expected time for A, we would go 4, so that's the A, plus, and then 4 times 5 plus, and then 12, and then divide that by 6. In the numerator we get 36, so that's 36 over 6 is 6. Okay, so here is the expected time for A. And now for B, we would have 1 plus 4 times 1.5 plus 5, and then divide all that by 6. In the numerator we have, let's see, that's 12. 12 on the top divided by 6, that gives us 2. Okay, and so forth. Now for the variance, you plug in 12 minus 4 on the top, divide that by 6, and square that. So in the parentheses, you're going to have 8 over 6, or 1.333, and then squaring 1.333 gives us 1.78. Just so, one more. For B, we would say 5 minus 1, and then 6, and square that. So that's 4 over 6, and then square the 4 over 6, giving us 0.44. Okay, and so forth, and so on. Now, even though that was really fun, but it could be tedious to do this calculation for all these activities. So now let's just use Excel to just fill in the two columns. Okay, here's a formula. So that's A plus 4 times 5 plus 12, following this formula here, and then close, divide by 6. Variance, we will have to have two parentheses, 12 minus 4, and then divide that by 6, and then square the whole thing. Now we could just copy down these formulas. Now we have those two columns filled in. Here we have the table already with the results of our calculation. Now we're going to draw the project network and then do our critical path analysis. Okay, so remember we start with a start node. Then we have A and B are the initial activities. Then we have, from A, we have C, D, and E. And from C to F and D to G. Now H has two predecessors, B and E. Let's put H here. And I has H as its predecessor. And J has F, G, and I as its predecessors. And that's it. So J must be the final activity. So we connect J to the finish node. Now for the activity times, we're going to use the expected durations here that we calculated. So 6, 2, 3, 5, 3, 2, 3, 4, 2, 2. Okay, and then we do our usual forward and the backward passes. Okay, and So we went through this before, so it should be easy for you guys to understand, right? So 9, 11, and 9 plus 2 is 11, 11 plus 3 is 14, and here we have two predecessors with a 2 and 9. Pick the higher value, and then plus 4 is 13, and I, we have 13 plus 2 is 15, and J has three predecessors, 11, 14, 15, highest value goes here, then 15 plus 2 is 17. Okay, so that was a forward pass. Now we go. Now from this we would say, oh, the total project time is 17 weeks. But it's not exactly 17 weeks, it's basically the expected value, because the times that we are using for the activities were not exact values, they were the expected values. So the total time we get will also be the expected values. So we would say from this number, we would say expected project time, not the exact project time, but expected time is 17 weeks. Okay, now we do the backward pass. So start with the 17, minus 2 is 15, 15 minus 2 is 13, 13 minus 4 is 9, and here we have 15, minus 3 is 12, 15 minus 2 is 13. Okay, copy down 13 here, 10, and here is 12. Minus 5 is 7, and here its successor is H. 9 is what we copy down, minus 3 is 6. Okay, for B we have 9, minus 2 is 7, and A we have 3 successors. So here it's, looks like this is 10, right? That's the 10, 7, and 6. 3 values to choose from, and remember we choose the smallest number, the 6. Then minus 6 is 0. So that's it. That's the end of the backward pass. From this we could see which the critical activities are. Alright, so here's A and E, basically the ones where the top and the bottom numbers are the same. Then we have H, I, and J. So we have a critical path of A, E, H, I, and J. And let's check to make sure the length of this path is the same as the 17 weeks. So that's 6 plus 3 plus H is 4, I is 2, and J is also 2. So that gives us 9 plus 4 is 13, plus 2 plus 2 is 17. Okay, so that checks out. So it looks like the 17 weeks is how long the project will take, but as I said before, this is not a definite number, this is just expected value. So project time T has a normal distribution. T, that is big T, not the little t. Big T has a normal distribution because it is a sum of the critical activity times. It has something to do with the central limit theorem. It has something to do with the central limit theorem, which says that even if the individual random variables, like the activity times, do not have normal distribution, if you average them or sum them, then the result tends to follow approximately normal distribution. Okay, so that means we could use what we know about normal distributions to do our calculation, like the probability, it'll be the probability that the project will be done by a certain time. Now again, for any distribution, we need to know the mean and the standard deviation, or the mean and the variance. Like, since variance and standard deviation, well, if we have one, you can always get the other. Okay, so we want to find the mean and the standard deviation. Once we have those, then we could do our probability calculation. Okay, so mu is the expected time, and that is a sum of the expected times for the critical path activities. And this is something we already did right here. So remember, these were the expected times for the critical activities, and we added them and got 17 already. So this is already obtained as 17. Okay, now the sum of variances of critical path activities, that we need to add up. So that means we pick out the critical activities and add the variances. That will give us the variance of the entire project time. So the critical activity variances are, here's a 1.78, and then E 0.11, H 0.69, I and J 0.03, 0.11. So these 5 values are what we want to add. So 1.78 plus 0.11 plus 0.69, 0311. So 1, 2, 3, 4, 5. Add them up. That gives us 2.72. Okay. Now to get the standard deviation, all we need to do is take the square root of this number. So that's going to be square root of 2.72, and that happens to be 1.65. So what we have is that we could say that project time has a normal distribution with a mean of 17 and a standard deviation of 1.65. So here's a picture of that distribution. T, big T for total time. 17 is the mean, so it's in the middle, and the interval, each interval here is the standard deviation, 1.65. So we have already answered the first 2 questions here. What is the mean project completion time? Is 17 weeks. Standard deviation of the project completion time was 1.65 weeks. Okay, now we need to ask these 2 questions. What is the probability the project can be finished in 20 weeks? In 20 weeks. Okay, well, how do we get that? So we need to do probability that the project time T will be less than or equal to 20 weeks. So, I mean, you wouldn't mind if you finished earlier than 20 weeks. That would still be considered finishing in 20 weeks. So we could say less than or equal to 20 weeks. And now how do you solve this? So what we want is 20 is about here. Very close to 20.3. So it's about here. And we're trying to find this area under the curve, area to the left of 20, all this area. Okay, and what we would do is we convert this 20 to the corresponding z value. So let's take a look at the z scale. Z, remember, is just the number of standard deviations away from the mean. So here is a z-scale, in the middle is a 0, here is 1 standard deviation above the mean, 20.3, z is 2, here is 3, and if you go below the mean, the z-scores are negative. Negative 1, negative 2, and negative 3. So what we want is, we need to just find the corresponding z value here. What is the z value? It's going to be 1 point something, close to 2. And how do you make that conversion? Is by this formula, x minus mu over sigma. So take the original number, subtract the mean, divide by the standard deviation. So here we could say, if I want the probability that t is less than 20, that would mean convert to z value, take the 20 original number minus the mean 17, divided by the standard deviation, which was 1.65. Okay, now that gives us 1.82. And this is a z-value we will look up in your z-table. Now, where is that z-table? Oh, that is in the next sheet, right here. Okay, so here we have the z-values to the first decimal digit, and the second decimal digit is listed here on the top. So we look for the 1.82 is going to look for the positive 1.82. That's here, and then 0.02 is the second decimal digit, so that's right here. 0.9656 then is the answer from 1.82. So here it was 0.9656. So this is our answer. So we could say we have about 97% chance of finishing by the deadline of 20 weeks. Okay, now let's take a look at the next question. The last question. Let's see. So here we already have 0.9656. Here it says, well, you're going to receive a bonus if you finish extra early, that is in 16 weeks or less. So here we want to know what is the probability of finishing within 16 weeks. Okay, so again, let's do this conversion. 16, that means the z-value is, again, take the original number, minus 17 divided by 1.65. Okay, and so that's going to be a negative value here. So negative value, negative 1 over 1.65, that is negative 0.606. Okay, so let's write it down. Negative 0.606. Now your z-table gives you area for the z-value within the second decimal digit. So we need to just round this to the second decimal digit. So we get negative 0.61 is what we want to look up. So the picture is like this. If this is a z scale here, negative 0.61. So that's somewhere on the left because in the middle is a 0. So here we have negative 0.61, and we're looking for this area. So this area is going to be smaller than 50%, smaller than half. So let's take a look. Negative 0.61, negative, so there it is, negative 0.6 and then 1. Here it is, 0.2709. Okay, so here we could say 0.2709 will be the answer. So about 27% chance, of getting that bonus. That is the answer. 2709. Okay, one thing I could mention here is, well, this is if you're using the table, using this z-table, but you could also, of course, use a Excel formula to get the areas under the curve. So for instance, here we could have said, so here's a formula. It's norm dot dist. So you could see it listed right here. It says returns a normal distribution for the specified mean and standard deviation. So let's choose that one. And then it says, tells you what to do. You gotta find 20 is the x, mean is 17, the standard deviation is 1.65, and the cumulative, it says, if you want the cumulative, that is, if you want the area under the curve, put true, or you could say 1. 1 is the same as true. And if you want the probability mass function, the probability mass function is just the height of this thing, not the area. And we hardly ever need it. But if you ever needed to find this height probability mass function, then you could put 0 here, or false, which is the same thing. False or 0 is the same thing. And the 1 and the true are the same things. Okay, and that gives us 0.96548. There's a slight difference here because our table shows you the area under the curve for the z-value rounded to the second decimal digit, and with the Excel function we don't have to worry about that. And here, just again for demonstration, we'll do the second one. So here was norm.dist, and then we have 16, 17 is a mean, 1.65 is standard deviation, and 1 is a cumulative, 1 for cumulative, and that gives us 0.27224. Again, similar but not exactly the same because of that round off issue with the z-value. And that's the end of the second example.